we can at least start the intro. So welcome everyone. Thank you for logging on and attending this evening's program. My name is Matt Schumann. I am on the programming team here at Cary Library. Before we begin, please let me know in the chat if you have any technical issues and I can hopefully try to resolve them for you. If you have any questions for our speaker, please submit them via the Q&A button and we will address them at the end. Sorry, my intro just went down. Keeps glitching. Okay. This program is made possible by the generous donors to the Cary Library Foundation and is in partnership with the Maynard Public Library, Belmont Public Library, Marlborough Public Library, and Tewksbury Public Library, who are all helping sponsor this program. With us this evening is Sangeeta Gautam. She's a NASA solar system ambassador and a mathematician by education, space explorer by curiosity, and a peace builder by passion. She has worked on 3 continents and always made time to empower the next generation through STEM activities wherever she goes. Sangeeta enjoys working in the community and brings people together to dialogue and explore space and its mysteries. She believes space truly unites us. Her goal is to engage the community in dialogue and make the world a better place for the children of the world. And toward this goal, she joined NASA /JPL as a solar system ambassador in 2021 and is the bridge between the community and NASA /JPL. So now please welcome Sangeeta.
Thank you, Matt. Good evening, everyone. So wonderful and delighted to have you all here today. Looking forward to exploring Jupiter and the workings of Juno and the learnings from Juno together with you today. So I'm not sure at what level all the participants are at, so I'm going to start at some little basic information, and then we'll grow from there into Juno's flyby of Europa. So with that, let's get started. So, we're going to be talking about Juno and Jupiter and what Juno's mission is and what it took for us to fly by. So let's see. Matt. Okay, I got it.
Yep, yeah.
I got it. Let me just get rid of this. So really how it all started in the beginning is, it is believed that the solar system really started out as a cloud of gas in our galaxy. And there were like probably other clouds that we see in the galaxy. And most of the clouds typically are made up of hydrogen and helium. And of course, there are different, so many numerous stars or the plasma that makes up this beautiful universe that we inhabit. So, it is believed that the sun was really born by by the collapse of spinning of the clouds, and that's how the sun was born. And it is also believed that the leftovers after the sun was formed, the leftovers really became Jupiter, and Jupiter is one of the biggest planets. And then the leftovers of the leftovers really became the rest, what we see in our solar system. So, there are so many theories about how our solar system was evolved. And there are, while there are many alternative theories that we believe is out there, and what we really, this whole goal of exploring Jupiter is to find out, get to the depths of it, and to really understand how exactly was the solar system formed. And as we'll see in upcoming slides, that Jupiter is really enriched with a lot of heavy elements, and it is also believed that the heavy elements that are really the seeds of Earth and the life that we know and live on, on this planet. So with that understanding, where it's really important to know where we came from and how we got here and how everything is made up. Of course, by now we know that everything is made up of atoms, and there is this quest to really compare. We are studying different planets, we're studying with the moon, the sun. For those who follow the different missions of NASA, you must have heard or followed or seen the solar probe that NASA sent for the solar probe of the sun. So there are different kinds, and the different comparisons of composition of the sun, planet, and the universe. That's all such it's a clue for us to really find out how we got here and what really makes up this solar system and the beautiful planet that we live on. So as we know that, Jupiter is the largest planet, and it is thought that it was probably the first one to be formed. And as we also know that Jupiter is really made up of all gas, and it's really hot, and of course the degrees vary where exactly in on the surface of Jupiter or inside. So it's very much the composition of Jupiter is thought to be a lot like Sun. But the thing about why we are so keen on Jupiter is the history of Earth has been lost. Like, a lot has changed, but Jupiter is still in its original form. So we can really, by studying Jupiter, we can learn a lot about our solar system, the formation, and really learn about how other planets and galaxies also work and operate. So, so the gravity of science and the water abundance, right? Those are the two things that some of the explorations that Juno really wants its goal is to answer questions like, does Jupiter have a core of heavy elements? What initiated the formation of Jupiter, and when was it? And what are the conditions in the protoplanetary nebula? And then also, because we want to study, as all of you are aware that, we are studying that where else does life exist? And so we're studying that how does the enrichment of oxygen compare with the other heavy elements, right? And how did the planets get their heavy elements? And how did Earth get its ocean and the volatiles? So these are the things that, we are curious about and we want to find out more about. And so then so that initiated our quest for Jupiter. And this is really a beautiful picture that was taken by the James Webb telescope. And so far, most of the telescope haven't been able to take such a picture from the land where, if you will notice, can you see my cursor?
Yep.
So if you see this ring, this is the Jupiter's ring, and this is one of the Jupiter's moon. So such a clear and a beautiful picture we were not able to get prior to James Webb. And if you'll notice these little white dots, these are the ammonia rings, the ammonia clouds. And this is what you really see as the red blob typically on Jupiter. And this blue that you see on top and over here is the aurora. So really a beautiful and an excellent picture of Jupiter. So really moving forward. So this is, Jupiter supposed to have like 60 to 70 moons, and most of them are really small, but there are 4 big ones. And I'm going to play a video right now to really explore. Let me know if you can hear it.
Yep, that's
Can you
perfect.
see it? Then I'll take it. So I really wanted to share that with you about how there's so many moons, but there are the 4 really big ones. And then when Juno flew by 3 of them. So this is the Galilean's discovery, right? Galileo, the astronaut, he really discovered that there are 4 big moons that Jupiter has, and that discovery led to really us then saying that, oh well, that much that we think that Earth is the center is not the Earth is not the center, right? And then of course that created a lot of controversy, but we really owe this finding to Galileo of these moons. And then if you'll see, so we flew by, Juno flew by Ganymede, Europa, and next it will fly to Io. So it is believed that, Europa, why we are really so excited about exploring and learning more about Jupiter, and especially Europa, is because Europa is considered to have twice as much water that Earth has. So we want to really explore that. Are the conditions in Europa really such that it will sustain life? And that is the key. So this is, something that not very many people know about. So when we sent Juno to Jupiter, we actually sent 3 special passengers with Juno. And this is, Galileo and Jupiter's wife, Juno. And then Juno is supposed to be the protector. And these are, of course, Roman mythology, come from Roman mythology. And these are Legos made up of aluminum, and they were placed inside of Juno. And then this plaque of Galileo's in his own handwriting, that was also put in here to honor him. So that was really beautiful. This piece of information was really interesting. So now we're going to watch a video on Jupiter. Why is it, sending Juno to Jupiter and the preparation that went into it wasn't really easy. And what were the challenges? What are the challenges? As I want to share a short video. For as we go through this session, you will see that you'll be able to relate that how much work went into doing in sending Juno.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. it's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. It just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
It's the biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about 1/3 of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we're going to go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. JOI.
Nothing's really certain about what's going to happen.
So I hope that brought to life the challenge that we have going to So the really the main reason for Juno to go explore there, like we saw some of it mentioned in the video, was we really need to determine what the origin of Jupiter was, determine the water abundance, the constraints, the core mass, and the alternative theories that we today know of. And we want to study the interior of Jupiter. And when we look at Juno and how it was, it has been built, you will see that how it is built to really measure the gravitational and the magnetic fields, because that is really important for us to know about how things are interacting in space with Juno and the particles in the orbit, and also what kind of atmosphere is there. And we will see later in today's session is, certain parts of Jupiter is like really hard, but certain parts are not that hard. So as you go deeper inside, it's harder, and it seems like from billions of years ago when Jupiter was formed, it is still cooling down. So it's so we want to really understand about what kind of atmosphere is it, and what is the magnetosphere. So all these things is what Juno's mission is to help us learn. And we'll see how it has shared so much data that we are able to determine not all of it, but a lot of it. So Juno's mission really, is to improve our understanding, of the giant planet, and by studying the Jupiter's origin, its interior structures, and the things that I just talked about. So Juno is solar powered, and the whole, and that's how it sustains itself in space as it is orbiting around. And we saw in the other video that Juno was launched in August of 2011, and Jupiter is really far, really far. It took us like 5 years to arrive in Jupiter, and now we are starting to we've started to explore the different moons and the different aspects, of Jupiter and its moons, and to learn a lot about how if Europa, especially that we're talking about today, is able to sustain life. So really, at a high level, one page, the mission is, that the plan was to do 32 polar orbits. And Juno goes around the poles of Jupiter, right? From the north to the south, and that's how it picks up measures the magnetic fields and all the data that is collecting. And for each orbit, it takes around 14 days. And the closest that Juno gets to it is, I think this was thought to be around 5,000 kilometers, but we went closer. And then the spacecraft spins, twice in a minute, right? So, and like I mentioned, that it is solar powered. And you'll see, I have another video of Juno, where you can see that how it really cartwheels as it goes around Jupiter. And then that cartwheel is, twice per minute. That's what it is. So this is the picture of Juno being really loaded into a C-17 and taken to Kennedy Space Center. That is where from where it was launched. And let's quickly watch this video. It's really fascinating to see how. And as I bring this, I had an opportunity to visit NASA and watch, be in that room, not during the launch of NASA.
This is Atlas Launch Control. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Juno spacecraft aboard an Atlas V rocket. Liftoff is from Launch Complex 41 at Cape Canaveral. The forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria.
It takes everything we know to get off this planet. So while everything that NASA does and building the Juno spacecraft and exploring Jupiter is all high tech, I think a rocket launch represents the extreme of that edge.
The energy in the room on launch day is stressful, but in a good way. It's a good feeling. It's almost electric. Everybody's excited and nervous, and I've seen people before, biting their nails.
A rocket launch is one of the most amazing things to see. I mean, it's truly a cosmic event.
Go. ULA safety officer. Go. Range, weather, and final clear to launch. Go. LC, LD, channel 1. Go ahead. LC, you have permission to launch. Roger.
The launch is probably our single biggest risk in the entire mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
When you see it, the first thing that you're impressed with is just the amount of energy. You feel it because the ground is shaking and you're miles away and the waves are coming through the ground like an earthquake would.
Mach 1.
You're canceling gravity. Gravity's pulling you down. You've got to get to a certain speed, and then that's the escape velocity to leave the Earth.
Max Q. Boosters throttling up. We're on schedule. Engine response looks good.
Watching something going from one planet to another.
And we have solids 1, 2, 3, 4, and 5 jettisoned. Visual indication that all solids have separated well. Current altitude is 45.8 miles in altitude, downrange distance 69 miles, velocity 5,413 miles per hour. And we have payload range jettison. And CFR jettison. We have retros and spacecraft separation. This concludes the plus count commentary for the AV-29 Juno mission.
It is so beautiful to be able to watch the launch. So this is this show talks about how Juno was built. So if you see that there are these three different the wings. These are about 8.5 meters long, and there is this this is the antenna, and the main focus of it's shaped like an umbrella, but its main focus is to really measure the gravity, and so it measure the gravity of Jupiter, and then of course whatever else it will pass by. Europa, it will measure that. Any other satellite it will pass by, it will measure that. And then these are the Jedi and the Jade are two these are sensors that are built in specially for measuring the aurora of of the satellites and Jupiter. And this is the magnetometer. If you see this has at the end, it's like a pin, and it's really stiff. And it has these cameras and sensors. And this is really used to measure the magnetic field of Jupiter and whatever satellites that it is passing by. And the data that is collected from here is really critical for all the determinations that NASA is using to make. And this is the MWR. It is the microwave radiometer. There are 6 of them. We see only one. And what this does is this actually helps us to measure the microwave the radiometer that will help us to go into the clouds, the cloud tops, and really measure the magnetic, the radiation, the microwave radiation in there. So this is really critical piece, and this was specially designed and invented for Juno. A lot of the things that are actually in the spacecraft is used from previous NASA missions, but this was really specially designed for Juno. And this is the Juno cam, which is the camera that is in Juno, which gets us all these beautiful pictures. And this measures the ultraviolet rays as we move past. And then this really looks at the infrared rays, and we're going to look at it in an upcoming slide. And this really measures the waves, and the data that we have, actually these waves of the sound were converted into sound. So I don't have those clips here today with us, but those clips, these waves, the information, the data that was collected is actually converted into sound. So that was really interesting. So we're going to watch a quick video. What was the video? Maybe it's on this one. So it's the same picture, but it shows, like how there are a lot of these information is gathered when it cartwheels Juno cartwheels, the data is collected in between these. But let me just show you really how it.
I've been asked in to help with the gravity science experiment. Measuring Jupiter's gravity depends on measuring changes in the spacecraft velocities that goes around Jupiter. What we're looking at is for variations in that acceleration rate that tells us something about the change in the gravitational field of Jupiter as it gets closer to the surface associated with a mass structure inside. And so what we're trying to do then is measure the spacecraft's velocity as a function of time very, very accurately. And we do that by measuring the Doppler shift of the radio signal. So if you've ever heard a fire engine going by with its siren, as it's approaching you, it's high pitch, and when it goes by, it goes, right? That Doppler shift, that change in pitch tells you about the velocity of the fire engine relative to you. So the instrument that we use is sort of a combination of the listening on the ground to the radio signal and the radio signal transmitted by the spacecraft. So the biggest part of the instrument, of course, is a 34-meter diameter radio antenna at Goldstone, California. Then on the spacecraft, there's a high-gain antenna that's pointed at the Earth. So the radio instrument measures the voltage coming in from the antenna from the Earth, and then it transmits a voltage that goes fed out to the radio signal to send back to the Earth. And then the gravity measurement tells us something about density variations, which then can tell us something about whether there's storms on the outside or whether they penetrate all the way through, and whether there's some hint of a structure at the center other than just compressed gas of the hydrogen.
So one thing, that there is a camera in here, which is called the Stellar. It's not mentioned here. It's called the Stellar Reference Unit. And that is really special because some of the, what it does is it has the ability to take pictures in very low light. And that is really important. Some of the pictures you'll see that in the upcoming slides, it's like gorgeous pictures that were taken by the Stellar Reference Unit. So, like we saw, like in some of the other videos, and the reason I've been sharing all these videos is to really, really bring to life, like there is so much, like the microwave radiometer that, that is there to really measure the thermal radiation, really trying to understand what is the atmosphere of that planet made of. And to be able to do that, we use the microwave radiometer for that. And then the microwave radiometer, the most important thing, and we'll see some slides on that, is really the pictures that it has taken of the Juno, of Jupiter's clouds, that form all the time. So we are the goal is to really investigate the atmospheric structure and also the gravity. Those are the two main reasons that we are there. And then if this is so we're really trying to understand the Doppler shifts, because what happens is when Juno passes by close to Jupiter or any other satellite, there is this magnetic field, and then there's this gravity. It shifts its orbit, and then and that data comes down to Earth, and then that helps us understand what is the mass based on that data, that what the object that Juno really passed, whether it's Jupiter or another satellite, what is the mass, like how dense it is, and it helps us understand and collect that data. So that's why it's like really important. And then this is again about the Jupiter's magnetic fields and how it allows us to probe deep, because we need to understand what is inside of that. And we are, Juno is is on a polar orbit from north to south, and really that allows us to map the magnetic fields on the polar on the poles. So Jupiter's magnetosphere is really near the planet poles. It's never been explored, right? So Juno is really is investigating that and providing us insight. And also, if you remember the picture that we had, that I showed, that was taken by James Webb, there were aurora at the top and the bottom, and then that's something that that we are trying to figure out. And there are electrically charged atomic particles along the magnetic fields that always crash into the atmosphere. And then when these crash into the atmosphere, that's when we see the auroras. And then there are special cameras. Remember the two cameras that we looked at, they measure the auroras. And in one of the videos earlier we saw that how challenging it is to Jupiter's environment is so challenging. It's really relentless, and the chances of any spacecraft surviving that kind of radiation, that kind of intense and severe environment is really hard. So this really highlights that Juno has all these critical electronics, and there's this around it is the walls of solid titanium, right? And so the goal is to really protect it from the intense radiation of Jupiter, and really allow these use of these designs. So a lot of, like I mentioned earlier, a lot of the electronics that NASA uses in its missions, it uses from whatever it can leverage from previous missions, it does that, and that's the same is true for Juno. The electronics that was used for Juno is also, a lot of them have been leveraged, and of course some are new. And then let's watch this video really quickly to get an idea of how it is going around.
Escaping the gravitational pull of Earth, Juno is still held to its trajectory by the Sun's gravity. The Juno spacecraft is carried 50 million miles into space, as far as the orbit of Mars. A burn from the main engine directs Juno back toward Earth for a final encounter with its home planet. Using Earth's gravity for energy, Juno slingshots into space, increasing its speed and receiving the boost it needs to pull away from the Sun and coast all the way to Jupiter.
It's really interesting how much thought went in to make that trip to Jupiter. So this is another quick one.
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. settling into the most challenging orbit ever attempted. Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year.
So it's really, really interesting. So let's talk about the Juno Europa flyby, which is really the topic of this session today. But you must be thinking, why I'm not talking about Juno flyby, Juno's flyby Europa. And really, the whole event happened in 13 minutes. So we'll see that right now. But this is a really special picture of Europa. And you'll notice that this is a picture of the terminator where the day and night, line is. And what you see, all these craters and these, fractures in the ice. So if you use a binocular to look at our moon, you'll see a lot of similarity. Of course, they're not same because this is all ice. And so Europa is thought that is covered with all ice, and beneath the surface is a salty ocean. This is the thought. We don't know yet, and we won't know yet until the Europa Clipper launches next year and sends us some data. But if you notice that, these fractures in the ice is really due to the tidal force. It's the squeezing of Jupiter's gravity and the cracking of the ice is what causes all these, is the cracks that you see. And this picture was really made by citizen scientist Vladimir Tarasov. And it's really beautifully captured. So so we've seen, and in many of in multiple videos so far, that there are the gravitational pull of Jupiter is like it's really strong, and it is so strong that it actually touches the orbit of Saturn. And so I want to just play this short video for you so you can really experience and see for yourself. Some of these is hard to just describe.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet in large magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it. Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. When we do this, over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere. A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Cunha years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before. We hope to learn more about how a magnetic field is generated by dynamo action deep in a planet's interior. For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
That was really incredible watching that. So this is Jupiter's. I'm not going to share a video on this just because of time. So this is when Juno entered from the North Pole. The top of the North Pole it looks like this. There are like 8 such, like the cyclones on top, and the formation is such that it's typically remains the same. Nobody knows why it's there or what isn't there or how they're formed. We don't know about that yet. But every so often, one of them will disappear, but then it comes back. So this is really the huge giant cyclones that are happening, and the yellow ones are really the hottest area. And let me go to the next slide. So if you see that these are the giant cyclones that are on Jupiter, and then these cyclones, these are like the yellow areas are the hottest, and the red ones are the medium, and the brown ones are the hottest. So and similar to what you see on the North Pole over here, in the South Pole you have like similar. It's more like an octagon, and there are like five of these. And similar to these in the North Pole, we don't know why they are 5 and why they are 7 and why they come and go. But this is what it looks. So this is this picture is from Juno, taking it from inside of Jupiter's rings. And this is the Jupiter ring. It's really dusty in here, and it is the thought is that the dust particles that we observe really come from Io, which is a volcanic moon, and also from the small moons colliding and other particles colliding, and then the dust materials. This is really really a dusty area in the rings. And this is the equator, and this is the halo. And these are the future, that we plan to, that Juno later would take these, go through these orbits. So if you look at, so this was a picture that was taken by Juno's, if you remember, there's this camera that we talked about, which the stellar reference unit. And this picture has been taken from, this is the Jupiter's ring, and looking away from Jupiter. And this is the Betelgeuse, and if you see, this is the Rhine's belt. And what this says is, no matter where that, the constellation that we see from Earth is the same constellation that you would see if you were in Jupiter or out there in space. So this is like really beautiful, and this was drawn out by NASA, mapping from the camera that we got. So what we've learned so far is Europa is really the smallest of the Galilean moons, and it's about the size of Earth's moon. Right? And like we know that the exterior is really all ice, and it is believed that underneath it is the salt water. And of course, we saw in the previous slide that it's thought that the water is twice as much as that on Earth. And none of this is proven, right? But it is thought that this is what, from the data that we have so far, is what we think it is. So here's what happened during the flyby. So, sorry. So we entered, Juno entered from around the equator, and then this is the first orbit that it made, and these are the earlier orbits that it made, and then it came into it came to Ganymede. But when NASA really worked with the Juno team worked very closely with the navigation team to really make sure that when it passed Ganymede was here, and that was on orbit 34. And then from it took a little over a year for Juno to then come by to Europa, which was orbit 45. And then from Europa, it is now going to Io, which is the next moon. And that is supposed to happen around on orbit 57, 58. And then from there, so you'll see that this is now Juno is on an extended mission, and then it'll come and into the main ring, and then that's how we will finish our the work that we're doing. And then so really flyby time, it was like really so short. So this is just a sketch of showing this is Europa, and this is Jupiter, and then we went through the north and came out from the south. So if you'll see that Juno got ready to before the flyby, because the spacecraft shakes a little bit. So before it took all the data, we waited for it to really settle down, and then at 2:50 it is right. It's by Europa. So it entered from the dark side and came out on the bright side. And so at 9:33, it doesn't see the Earth, right? It enters the Earth occultation, and then on 9:33, just a few seconds later, it enters solar eclipse, right? And then really, and then it closest, it goes up to as close as 358 kilometers at 9:36. 3 minutes later, it is by Europa. And then just a few seconds later, it exits the Earth occultation, and then it exits the solar eclipse, and then it exits the solar eclipse at just a few seconds later. And then Europa, it leaves Europa and it's back in the normal altitude. So you'll see that, the whole thing, Europa flyby was a 13-minute deal. And then it just went, and then it went towards Jupiter. So it happened like so fast. It really happened fast. And during that time, it took just these 4 pictures. And if you'll see that these up top, all these are supposed to be the salts or the minerals that have come up on the top, and they've changed color because of the radiation. So if you'll see there's the crater, and that crater's turned around. So it happened so quickly. It was just those 4 pictures. And then the study shows that, then you really enlarge these, and then scientists really study all the details of Europa. Are gonna move fast. And then these are these little shiny objects that you see. Those are actually the radiations on the camera, and it's like so harsh that it just goes in and comes out to be able to survive. So this is how it is. We've talked about this before, so I'm not going to spend a lot of time. And this is how Europa is supposed to have the ocean beneath. Then there's a warmer ice and the really stiff ice that we see up top on Europa's surface. Next, what we're going to explore, the mission is Io, which it is expected that Io is the next moon. We will be there in December of this year. And so next year in 2024 in October, Europa Clipper is being, that is another spacecraft that is actually going to explore the habitability, that whether we can live there in Europa or not. So that is the mission of Europa Clipper. And this is something for, I'm going to put this in the chat. What you can do is you can put your name here, and NASA will send your name with Europa Clipper next year up into Juno. So thank you so much. Sorry, it kind of went a little over, but I appreciate your time here. Thank you.
No, it's absolutely fascinating, and thank you so much for explaining all of this. I just want to remind people, if you want to ask a question, please submit it via the Q&A. It looks like we already have some that are coming in, but please feel free to send some in. So one question here is, why is there so much radiation when it is so far from the sun? Is there no atmosphere to diffuse it like on Earth?
Jupiter is all gas, and a lot of information, like we don't know yet, but we know that there are so many. It's really because Jupiter is all gas and it has like really huge gravity, but we don't. A lot of that information is we don't have.
Mm-hmm.
Hi, Stephen from Neptune. I like that.
Yeah, there's a couple people, someone from Cambridge, Tenafly, New Jersey, Westport, Connecticut, so people from all over. The next question is, will the Europa Clipper try to orbit Europa and land on it?
Yeah, that's the plan, is to be able to to really study if we can go live there and how habitable it is. And it is all because the understanding is that life on Earth started from the ocean. And so because Europa has salty water underneath the ocean water, we think it is salty, but we don't know until Clipper goes and really gets us all that data. But yeah, that's the plan, to be there and explore habitability. And
yeah,
so probably in a couple of years, we all can move to Europa.
Have there been any surprises along the way so far?
No, it seems like Juno is really doing great. They don't have any, they don't see any degradation. I think one of the concerns was, and that was a concern really from the planetary protection, requirement, that Juno should not bump into Europa, because if it bumps into Europa, it's going to contaminate Europa, and so. But now that initially that was a concern, but that's not a concern because we've flown by Europa, and now we're by Jupiter, and we have no intention or the mission, as a part of the plan, Juno's plan, to go back to Europa. So, so I think, yeah, that's so far, we haven't seen any or heard about any mishaps.
Yeah. I think this next question, I think you did talk about this, but if Jupiter, somebody asked, if Jupiter is like the sun, does it emit visible radiation?
It has a lot of radiation, and that is why if, in one of the slides I showed that on the camera, that there's a lot of radiation, and that's and if initially when Juno went there, it was like people were concerned because of that strong radiation. Will it survive? Because there hasn't been any spacecraft that's been there, so it does have really strong radiation.
Yeah, so this is the first ship to ever actually go in. That was another question that was there, but there's another that came in. Do scientists surmise that the conditions in Europa's ocean may contain the building blocks of life?
That's the hope. That's why we are spending so much time, sending Clipper, Europa Clipper. It is really, we have a lot of hope because of the water, and it's salty water, we think. So we don't know yet, but we are hoping that it turns out that there is life, because that's how it started on Earth.
Yeah. Do you have time to take a couple more questions?
Sure.
Yeah. Okay. Well, I guess just going off the water question, what would the temperature of the water on Europa be?
I have to make a guess, and I don't want to make a guess. I don't know. I think I haven't seen that data, but I'm going to make a note of it.
Yeah.
Because right now, I think all these Juno, what it is doing is because with it's the remember the MWR that was invented just for Juno. It is really sensing just the cloud tops of Jupiter. And remember that antenna on the top that does the gravitational. So they are measuring. These are so designed. Most of these instruments in Juno are so designed that they can do both the hot and the cold. So it's collecting some data on Europa, but we don't have the exact temperature data.
Yeah. What did it cost to build Juno?
I have no clue. I'm gonna find that out.
And then maybe the last question could be, is Jupiter the most important planet for blocking asteroids from hitting Earth?
So I think for Jupiter is important, not so much in, I would say, for the asteroid, because asteroids seem to be coming from other places so far that NASA has been deflecting, but mostly because that will tell us how planets are formed, because that was the next, that is the biggest planet, and it's so much so like sun. So it will tell us reveal a lot of those mysteries. But for the asteroid question, I don't know, we're gonna find out together, but that I haven't heard about Juno, about asteroids from Jupiter so far.
Great. Well, I want to thank you so much for taking time out of your evening to talk about all this with us. And if there are people on Jupiter, or Jupiter could thank you, you're a wonderful spokesperson for the planet. But thank you so much.
Oh, thank you so much. I appreciate it. I enjoyed speaking with everybody, and thank you so much for attending. Thank you so much for all the questions. I enjoyed. Well, thank you, Frank. Thank you, everybody. I really appreciate this opportunity. Thank you, Matt. Please thank Helen.
Yes,
it was wonderful.
All
Thank
right.
you.
Have a good night, everyone.
Have a good evening, everybody. Take care. Thank you. Thank you, everybody, for all the comments. I appreciate that.
Thank you, everyone.
Take care.